Hello there and welcome back to the Science Sleepy Minds. You're drifting. Right now, in this very moment, you are hurtling through the cosmos at approximately 600 kilometers per second relative to the cosmic microwave background radiation. You probably did not feel that. You never do. The Earth spins beneath you, carrying you through its orbit around the Sun, while the Sun itself careens around the Milky Way center, and the Milky Way rushes towards something astronomers ominously call the Great Attractor. All of this motion, all of this cosmic choreography, and you are lying there, perhaps under a blanket, perhaps with a pillow that has somehow already migrated to an uncomfortable position. Tonight we're going somewhere extraordinary. We're going to the very beginning, not the beginning of your day, not the beginning of human civilization, not even the beginning of Earth itself. We're going to the moment before moments existed, to the instant when everything, every atom that would eventually become stars, planets, oceans, dinosaurs, your favorite coffee mug, and yes, even you, came screaming into existence. And here is the twist that might keep you awake for at least a few more minutes. Some physicists believe our entire universe erupted from something called a white hole. You probably will not survive this journey in any meaningful physical sense, but that is perfectly fine because neither would any spacecraft, any probe, or any theoretical being we could imagine. The conditions we're about to explore would vaporize matter itself, would stretch time into taffy, would make the laws of physics throw up their metaphorical hands and admit defeat. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. I would love to know where you're listening from tonight. Drop your location and local time in the comments. Are you in Tokyo watching the city lights flicker through your window, perhaps in Sao Paulo with the distant hum of traffic still audible? Maybe somewhere in rural Canada where the stars actually look like the universe is showing off. Wherever you are now part of this strange little community of people who enjoy falling asleep to discussions about the fundamental nature of reality. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Picture yourself floating in absolute darkness. Not the darkness of a room with the lights off, where photons still bounce around from streetlights and electronic devices. This is the darkness of true nothing. No light exists here because light itself does not yet exist. No space stretches out around you because space has not been invented. You're somehow present at the absence of presence, witnessing the void that preceded everything. And then, though then is a meaningless word when time itself is not yet ticking, something happens. The idea that our universe might have emerged from a white hole sounds like science fiction, and you would be forgiven for thinking some physicists simply had too much coffee and let their imagination run wild. But this concept has roots stretching back to the 1960s, when theorists first began seriously exploring what happens when you run the equations of general relativity backward. You see, Albert Einstein's magnificent framework for understanding gravity does something peculiar. It works equally well whether time moves forward or backward. The mathematics do not care about your birthday candles marking another year gone. The equations are, as physicists say, time-symmetric. In 1964, Russian physicist Igor Novikov formally introduced the concept of white holes to the scientific community, though the mathematical possibility had been lurking in the equations for decades. Novikov was not claiming he had discovered a new type of celestial object. He was pointing out that if black holes could exist, regions of space-time where gravity becomes so intense that nothing, not even light, can escape, then the equations also permitted the existence of their opposites. Scholars still argue whether Novikov was the first to truly articulate this concept, or whether the idea had been floating around in more fragmented forms throughout the theoretical physics community. Scientific priority is always messier than textbooks suggest. Here is something delightfully strange to consider. While black holes have become almost mundane to us now, captured in photographs and featured in Hollywood blockbusters, we have never observed a white hole. Not once. Not a single confirmed detection in the entire history of astronomy. This is either because they do not exist, because they are extraordinarily rare, or because they existed only once at the birth of our universe, and we have been living inside one ever since. Let that thought settle into your mind as you sink deeper into your pillow. You might be inside a white hole right now. The space around you, the air you're breathing, the planet beneath you, the stars above you, all of it potentially the interior of a cosmic object that physicists once dismissed as a mathematical curiosity. The journey from interesting equation artifact to possible explanation for the origin of everything has been a strange one, and we're going to walk it together tonight. We will meet brilliant minds who have devoted their careers to understanding these concepts. We will encounter paradoxes that seem to break logic itself. We will ask questions that have no definitive answers and find, perhaps, that the uncertainty is the most beautiful part. Your eyelids are already growing heavy, are they not? That is perfectly acceptable. The universe took approximately 13.8 billion years to create the conditions for you to exist and feel sleepy. It would be rude not to honour that effort. The distinction between black holes and white holes is, at first glance, almost comically simple. A black hole swallows, a white hole spits. If a black hole is the universe's most terrifying drain, sucking in everything unfortunate enough to wander too close, then a white hole is the opposite, a cosmic fountain, perpetually spewing matter and energy outward, refusing to let anything in. You can imagine standing near a black hole, though standing is a generous term for what your body would actually be doing in such intense gravitational fields. Everything around you would be falling inward. Light would curve toward the central point. Space itself would be flowing like a river toward an infinite waterfall. The event horizon, that famous boundary of no return, marks the point where the flow of space exceeds the speed of light. Nothing can swim upstream faster than light, so nothing escapes. Now flip that image. You're near a white hole and everything around you is rushing outward. Light is being pushed away. Space is flowing like a river moving in the opposite direction, away from the centre. There exists an event horizon here too, but it works in reverse. Nothing can enter. You could fire the most powerful rocket engine ever conceived directly at a white hole and watch helplessly as the very fabric of space-time pushed you back. The current is simply too strong. This is where the mathematics become genuinely fascinating, and I promise to keep the equations themselves tucked away where they cannot hurt you. When Carl Schwarzschild first solved Einstein's field equations for a spherical, non-rotating mass in 1916, he discovered something remarkable. His solution described what we now recognise as a black hole, but buried in that same mathematical framework was an embarrassing sibling, the white hole solution. Schwarzschild himself did not live long enough to fully explore these implications. He died just months after publishing his groundbreaking work, a victim of a rare autoimmune disease contracted while serving in the German army during World War I. The trenches of that war seem impossibly far from the abstract beauty of curved space-time, yet Schwarzschild managed to solve Einstein's equations while calculating artillery trajectories. Scientists still argue whether his early death robbed physics of even greater discoveries, or whether his foundational work was contribution enough for any lifetime. The peculiar thing about Einstein's equations is that they describe relationships between matter, energy, and the curvature of space-time without any built-in preference for which direction time flows. If you film a ball rolling down a hill, and then play the footage backward, you see a ball rolling up a hill. Both scenarios obey the laws of physics. Classical mechanics does not care about the arrow of time in its fundamental equations, even though our everyday experience suggests time very much moves in one direction. General relativity inherits this time symmetry, The equations that predict a black hole forming from a collapsing star work equally well if you reverse the time direction, run the movie backward, and that collapsing star becomes an exploding one. The black hole becomes a white hole. The mathematics cannot tell the difference, which is either profound or deeply annoying depending on your philosophical inclinations. Here is a quirky historical detail that rarely makes it into the textbooks. When physicists first started taking white holes seriously in the 1960s, some genuinely proposed that quasars, those incredibly luminous objects at the centers of distant galaxies, might be white holes in action. The energy output was so staggering, the brightness so incomprehensible, that a few researchers thought perhaps they were witnessing matter streaming out of white holes rather than falling into supermassive black holes. This interpretation did not survive contact with additional data, but it represents a charming moment when the boundary between wild speculation and legitimate hypothesis was particularly blurry. Modern astronomers have thoroughly established that quasars are powered by black holes, not white holes. The matter spiraling into those gravitational monsters heats up to extraordinary temperatures before crossing the event horizon, emitting the light we detect across billions of light years. The energy comes from the death of matter, not its birth. And yet the white hole idea refused to die completely. You might wonder why physicists bother thinking about something they have never observed. This is a fair question, and the answer reveals something important about how theoretical physics operates. The field is not strictly about describing what we see. It is equally about exploring what the mathematics permit. If an equation allows for a particular phenomenon, physicists want to know why that phenomenon does or does not appear in nature. The absence of white holes is almost as interesting as their presence would be. Something is preventing them from existing, or making them so rare as to be undetectable, or confining them to circumstances so extreme that we would never recognize them. Or perhaps we have already found one. Perhaps the most spectacular white hole in existence is not some distant astronomical object, but the entire observable universe itself. Perhaps the Big Bang was not just metaphorically similar to a white hole, it was one. This hypothesis sits at the intersection of cosmology and general relativity, two fields that have achieved tremendous successes but still harbour deep unresolved tensions. Cosmologists study the large-scale structure and evolution of the universe. Relativists study the geometry of space-time. When these disciplines converge on the question of cosmic origins, the results are either illuminating or headache-inducing, often simultaneously. You do not need to fully understand the mathematics to appreciate the poetry here. Imagine that black holes in some other universe, some parent cosmos we can never observe, collapse and, through mechanisms we barely comprehend, give birth to new universes. Each baby universe emerges through a white hole. Our Big Bang was such an emergence. We're living in the aftermath of a cosmic birthing event, surrounded by the expanding debris of whatever collapsed elsewhere. The thought is enough to make your head spin, which is probably good because spinning leads to dizziness, and dizziness leads to lying down, and lying down leads to sleep. Let the concepts wash over you. Einstein's equations running both ways sounds like an abstract mathematical curiosity, the kind of thing that physicists discuss over coffee and then promptly ignore when doing actual calculations. But this time, symmetry has profound implications that reach far beyond chalkboard exercises. It touches on questions about the nature of reality itself, about whether the universe has fundamental preferences, about what distinguishes past from future in a cosmos whose basic laws seem not to care. You're lying there, breathing slowly, and your breath is an excellent example of time's arrow in action. You inhale, oxygen enters your lungs, diffuses into your bloodstream, fuels cellular processes, and eventually you exhale carbon dioxide. This sequence only happens in one direction, You never accidentally inhale carbon dioxide and exhale oxygen. Your lungs do not spontaneously reverse their function. Time for your respiratory system moves stubbornly forward. But zoom into the level of individual molecules, and the picture becomes murkier. Each collision between oxygen molecules and the membranes of your lung tissue obeys equations that work perfectly well in reverse. A physicist watching a single molecular interaction could not tell you, from the physics alone, whether the movie was playing forward or backward. The arrow of time emerges from statistics, from the overwhelming probability that systems move toward greater disorder, not from any fundamental asymmetry in the laws themselves. General relativity is no different. The equations Einstein published in 1915 describe how mass and energy curve space-time, how objects move along the curves that other objects create, how the geometry of the universe evolves. These equations are differential equations, relating rates of change to current states, and they work identically, regardless of whether you define time as increasing toward what you call the future or toward what you call the past. Carl Schwarzschild exploited this mathematical framework brilliantly. Working from Einstein's newly published theory, he found exact solutions describing the space-time around a spherical mass. His 1916 paper was a landmark achievement, the first exact solution to Einstein's field equations, and it revealed the possibility of what we now call the event horizon, a surface surrounding sufficiently compressed mass from which nothing can escape. Scholars still argue whether Schwarzschild fully appreciated the radical implications of his own solution. He was primarily interested in describing the gravitational field around stars and planets, practical applications for astronomy and celestial mechanics. The more exotic features of his solution, the event horizon, the central singularity, the time reversal implications, were mathematical curiosities that would take decades to properly understand. Here is a delightful piece of historical trivia. Einstein himself was initially skeptical that black holes could actually form in nature. He published a paper in 1939 attempting to prove that matter could not collapse to such extreme densities. The argument was clever but ultimately flawed, relying on assumptions about how matter behaves under extreme pressure that turned out to be incorrect. Even geniuses get things wrong sometimes, which is oddly comforting when you're struggling to understand concepts that confused Einstein. The time reversal symmetry of Schwarzschild's solution means that mathematically, you can start with a black hole and simply flip the direction of time. Where matter was falling in, it now falls out. Where space was flowing toward the singularity, it now flows away. The event horizon changes from a one-way entrance to a one-way exit. Every property inverts, and you have a white hole. For many years, physicists treated white holes as mathematical ghosts, technically permitted by the equations but presumably excluded by some other principle not yet fully articulated. Nature, the thinking went, must have reasons for preferring black holes over white holes. Perhaps thermodynamics forbade them. Perhaps quantum mechanics rendered them unstable. Perhaps they simply could not form through any realistic process. But then people started thinking more carefully about the Big Bang, and the white hole hypothesis crept back into serious discourse. The Big Bang singularity has always been troublesome. At time zero, according to standard cosmological models, all the matter and energy in the observable universe was concentrated in a single point of infinite density. Space itself was compressed to nothing. The equations of general relativity break down completely at such conditions, producing infinities that physicists call singularities. These are not physical objects, but rather signals that the theory has reached its limits, that some new physics must take over where general relativity fails. Now consider what emerges from this singularity. Matter and energy explode outward. Space expands in all directions. The universe rushes away from its own origin with no possibility of returning. Does this not sound remarkably like the description of a white hole? Matter streaming outward, space flowing away from the centre, an event horizon in reverse. The analogy is not perfect, and we will explore its limitations as the night progresses. But the resemblance is striking enough that serious cosmologists have devoted careers to investigating whether the Big Bang was in some meaningful sense a white hole event. If so, we are not merely living in a universe that began with conditions similar to a white hole. We are living inside a white hole, experiencing its interior from the only perspective possible, from within. Your position in bed is your position within this hypothetical cosmic object. The walls of your room, the ceiling above you, the floor below, all of it interior to a white hole that has been expanding for nearly 14 billion years. The stars you might see through your window, if you're fortunate enough to have a clear sky, are fellow travellers within this same interior, moving with the flow of space-time away from an origin we can never revisit. The Big Bang has a suspicious resemblance to white hole behaviour that once you notice you cannot quite ignore. Both involve matter and energy erupting from a singularity. Both feature an event horizon of sorts, a boundary beyond which we cannot peer. Both produce expansion, the outward rush of space and everything within it. The parallels are either coincidental, deeply meaningful, or somewhere in that frustrating middle ground where scientific consensus has not yet formed. You're breathing more slowly now, perhaps, settling into the rhythm of rest while contemplating the origin of everything. The irony is not lost here. You're winding down for the night while the universe, that vast cosmic entity we call home, has been winding up since its inception. Expansion continues. Galaxies recede from each other. Space itself stretches, carrying matter along for the ride. Standard cosmological models describe the Big Bang as a hot, dense state from which the universe evolved. This is technically accurate, but perhaps misleading in its passivity. The universe did not merely evolve from the Big Bang like a flower growing from a seed. The universe exploded from the Big Bang, with matter and radiation streaming outward at velocities approaching the speed of light, with space expanding so rapidly that in the first fraction of a second, the universe grew from a point smaller than an atom to something larger than the current observable universe. This expansion is one of the features that most closely matches white hole descriptions. When matter crosses a white hole's event horizon moving outward, it can never return. The geometry of space-time forbids it. Similarly, regions of the universe that have receded beyond a certain distance from us can never be reached again, even travelling at the speed of light. The expansion of space itself carries them away faster than any signal could catch up. Astronomers call this boundary the cosmological horizon, and it functions remarkably like an inverted event horizon. A black hole's event horizon marks the boundary beyond which nothing inside can escape. The cosmological horizon marks the boundary beyond which nothing outside can enter. We are trapped within, able to observe only a finite volume of what might be an infinite universe, cut off from regions that have expanded beyond our causal reach. Here is a mainstream historical fact that deserves attention. The discovery of cosmic expansion was one of the most significant scientific achievements of the 20th century, yet it was initially resisted by Einstein himself. When astronomer Edwin Hubble presented evidence in 1929 that distant galaxies were receding from us at velocities proportional to their distance, Einstein abandoned his cosmological constant, a mathematical term he had added to his equation specifically to prevent expansion, calling it his greatest blunder. The universe was expanding, whether the mathematics originally expected it or not. Scholars still argue whether the cosmological constant truly was a blunder, or whether Einstein's physical intuition was simply ahead of the observational evidence. Modern cosmology has actually reintroduced a cosmological constant, or something mathematically equivalent, to explain the accelerating expansion discovered in 1998. Perhaps Einstein was wrong for the right reasons, or right for reasons he did not fully understand. The singularity at the heart of the Big Bang presents another parallel to white holes. Black holes contain singularities at their centers, points where density becomes infinite and the curvature of space-time becomes unmeasurable. General relativity cannot describe what happens at a singularity. The equations produce infinities, which is mathematics' way of saying I give up. Please try another theory. White holes, as the time-reversed versions of black holes, would also contain singularities. But these singularities would be in the past rather than the future. A black hole singularity is something you fall toward, an inescapable fate awaiting anything that crosses the event horizon. A white hole singularity is something you came from, an inescapable origin from which everything emerged. The Big Bang singularity has precisely this character. It lies in our past at time zero, as the origin point from which all matter and energy emerged. We did not fall toward it, we came from it. Our entire cosmic history is the aftermath of that emergence, the expansion of everything that once was compressed into that singular point. Some physicists find this resemblance too striking to be coincidental. If white holes are real, and if the Big Bang has all the properties of a white hole, then perhaps the simplest explanation is that they are the same thing. Our universe did not merely begin in a state similar to a white hole interior. It began as a white hole interior. We are living in the expanding output of a white hole that has been spewing matter and space and time for 13.8 billion years. A quirky fringe detail adds colour to this picture. Some theorists have speculated that white holes might be inherently unstable, existing only briefly before converting into black holes or dissipating entirely. If so, our universe might be an exceptionally long-lived white hole, one that somehow avoided the instabilities that would destroy others. Or perhaps universes, being infinite in extent and eternal in their own reference frame, do not experience the same instabilities that would affect localized white holes in otherwise empty space. The mathematics here becomes subtle in ways that matter for specialists but need not trouble your relaxing mind. What matters for our journey is the conceptual picture, a universe that began from something remarkably similar to what physicists define as a white hole, expanding from an infinitely dense singularity, pushing matter and space outward, creating the cosmos we now inhabit. Your heartbeat has probably slowed by now. The rhythm of your blood, pumped by an organ that has been beating since before you were born, mirrors in miniature the pulse of the cosmos. Expansion and contraction, systole and diastole, the universe and your heart both participating in the ancient dance of pressure and release. Singularities are where physics goes to have an existential crisis. They are the mathematical equivalent of throwing up your hands and admitting that the current framework simply cannot handle what is happening. Every time a singularity appears in an equation, it signals that somewhere, somehow, the theory has been pushed beyond its domain of validity. Something else must take over, but we do not always know what that something else might be. You encounter gentler versions of this phenomenon in everyday life. Consider the tip of a very sharp needle. As the point becomes infinitely small, the pressure it can exert becomes infinitely large, at least according to the simple formula pressure equals force divided by area. In practice, no needle is infinitely sharp, so the singularity never actually manifests. The atomic structure of matter provides a natural flaw, a minimum size below which needles cannot be sharpened. Black holes are not so forgiving. General relativity predicts that matter, collapsing under its own gravity, will compress to ever smaller volumes until it occupies zero space, a point of infinite density at the center of every black hole. This is the singularity, the place where the curvature of space-time becomes infinite, where the equations produce nonsense answers, where our understanding reaches a hard wall. White holes inherit this problematic feature. Since they are time-reversed black holes, their singularities are also time-reversed. Instead of being the endpoint toward which everything collapses, the white hole's singularity is the starting point from which everything emerges. It is an origin singularity rather than a destination singularity. Both are equally troublesome from a mathematical perspective. The Big Bang singularity shares this character. At time zero, all matter and energy in the observable universe occupied zero volume with infinite density. The equations of general relativity confidently describe what happens after the first instant: expansion, cooling, the formation of particles and eventually atoms, but they fall silent about the singularity itself. What was happening at time zero? What conditions prevailed at infinite density? The theory cannot say. Here is a mainstream fact that shapes our understanding. The singularity theorems proven by Roger Penrose and Stephen Hawking in the 1960s and 70s demonstrated that singularities are not merely mathematical artifacts, but genuine predictions of general relativity. If the universe began in a state of compression, a singularity is unavoidable given reasonable assumptions about matter and energy. You cannot finesse your way around it with clever initial conditions. The singularity is baked into the mathematics. Scholars still argue whether these singularity theorems imply that singularities actually exist in nature, or whether they instead demonstrate that general relativity must be replaced by some more complete theory at extreme scales. The theorems prove that general relativity predicts singularities, but general relativity might simply be wrong in those extreme conditions. Quantum effects, presumably, take over where classical physics fails. This is where the story becomes genuinely strange. Quantum mechanics and general relativity are both spectacularly successful theories within their respective domains. Quantum mechanics describes the behavior of particles at tiny scales with exquisite precision. General relativity describes the behavior of gravity at cosmic scales with equal accuracy. But the two theories refuse to play nicely together. Attempts to combine them, to create a quantum theory of gravity, have produced partial successes but no complete framework. At singularities, both theories should be relevant. The density is high enough that gravity is extreme, requiring general relativity. The distances are small enough that quantum effects should dominate, requiring quantum mechanics. The two theories clash at precisely the point where we most need them to cooperate. A quirky fringe detail illuminates the stakes. Some theorists have proposed that singularities might be cosmic censorship mechanisms, hiding the breakdown of physics behind event horizons, where we can never observe it directly. The interior of a black hole, including its singularity, is forever hidden from outside observers. Whatever happens there, whatever embarrassing failures of theory might occur, remains private. The universe, in this view, is modest about its limitations. White holes pose a different challenge to cosmic modesty. If singularities are meant to be hidden, white holes are exhibitionists. Their singularities would be visible from outside, accessible to observers who could watch matter streaming out from a point of infinite density. The equations would break down in plain view. The failures of physics would be on public display. This visibility is one reason physicists have long been skeptical about white holes. The universe seems to prefer hiding its singularities, wrapping them in event horizons where embarrassing infinities cannot be observed. White holes violate this preference. They are cosmically immodest. But the Big Bang singularity is also in a sense visible. We cannot observe it directly, but we can observe its consequences. The cosmic microwave background radiation that fills the universe is an echo of conditions shortly after the singularity. The distribution of galaxies across the sky reflects the initial conditions that were present near time zero. We're constantly observing the aftermath of a naked singularity, and somehow the universe has not collapsed from the embarrassment. Perhaps the Big Bang singularity is uniquely permitted to be visible because it is inside us rather than outside. We're not looking at it from a distance. We're surrounded by it, embedded within its expanding output. The singularity is not somewhere else, observable through a telescope. The singularity is everywhere and everywhen, the shared origin point from which everything emerged. Let this thought drift through your mind as you settle deeper into relaxation. You're not separate from the singularity. You're its legacy, its consequence, its distant descendant. The infinite density of time zero has spread and cooled and eventually formed you. Lee Smolin stared at the equations and saw something that would reshape his career. What if black holes do not merely destroy matter, but transform it? What if the singularity at a black hole center is not an endpoint but a doorway? What if collapsing matter in one universe could give birth to an entirely new universe, emerging through a white hole into virgin space-time? You have encountered doorways throughout your day, passing through frames that separate one room from another. Smolin's doorways are considerably more dramatic. They separate one cosmos from another. They connect parent universes to their offspring. They transform destruction into creation through mechanisms that remain speculative but tantalizingly plausible. The hypothesis Smolin developed, beginning in the 1990s, bears the name cosmological natural selection. The terminology deliberately echoes biological evolution, and the parallel is not merely poetic. In biological natural selection, organisms that survive and reproduce pass their characteristics to offspring. Offspring vary slightly from parents, and those variations that enhance survival and reproduction spread through future generations. Over time, populations evolve toward configurations that are good at producing copies of themselves. Smolin proposed that universes might work similarly. Imagine a universe containing physical constants, the strength of gravity, the mass of electrons, the speed of light, that permit the formation of black holes. Each black hole, upon collapsing, spawns a new universe. The offspring universe inherits the parent's physical constants, but with small variations, mutations in the fundamental parameters that define how physics works. Some offspring universes will have constants that make black holes rare or impossible. These universes will produce few or no offspring of their own. Other offspring universes will have constants that make black holes abundant. These universes will be prolific parents spawning many offspring who inherit their black hole-friendly parameters. Here is the mainstream historical fact anchoring this speculation. Smolin was not inventing the idea of the multiverse from nothing. Cosmologists had been discussing multiple universes for decades, motivated by the strange fine-tuning problems that plagued fundamental physics. Why does our universe have physical constants so precisely calibrated to permit complex structures, stars, planets, chemistry, and eventually life? One answer is that countless universes exist, each with different constants, and we necessarily find ourselves in one of the rare configurations compatible with our existence. Cosmological natural selection offers a different answer. Our universe has life-friendly constants, because life-friendly constants happen to correlate with black hole-friendly constants, and black hole-friendly universes outproduce their less fertile siblings. The fine-tuning is explained not by anthropic selection. We exist because we must exist somewhere, but by evolutionary dynamics favouring certain cosmic configurations over others. Scholars still argue whether this hypothesis is testable in any meaningful sense. Scientific theories are supposed to make predictions that could, in principle, be proven wrong. What predictions does cosmological natural selection offer? Smolin suggested several. Our universe should have parameters optimized for black hole production. If we could slightly change physical constants in ways that would increase black hole formation, we should find that such changes would destabilize other features of physics. The universe should sit at a local maximum in the landscape of black hole productivity, unable to improve through small variations. A quirky fringe detail adds intrigue to the story. Smolin specifically proposed that our universe should not be able to produce more black holes if neutron stars were slightly more massive. Astrophysicists have been accumulating data on neutron star masses for decades, and the results are tantalizingly close to Smolin's predictions. The most massive neutron stars sit just below the threshold where they would collapse into black holes. If that threshold were slightly different, more black holes would form. This is exactly what cosmological natural selection predicts. The mechanism connecting black hole collapse to white hole emergence remains deeply speculative. General relativity does not provide a clear pathway from one to the other. The singularity at a black hole's center is where the equations break down, where we need some theory of quantum gravity to tell us what actually happens. Perhaps matter is truly destroyed at singularities, perhaps it bounces back, perhaps it tunnels through to somewhere else entirely. Loop quantum gravity, a candidate theory for quantum gravity that we will explore soon, suggests the bounce interpretation. When matter reaches sufficiently extreme densities, quantum effects prevent further compression. The collapse reverses. What was falling in begins exploding out. The black hole transforms into a white hole, and if that white hole opens into a separate region of space-time, a new universe is born. You're perhaps 3 or 4 universes removed from whatever began this cosmic lineage, assuming the hypothesis is correct. Your great-great-grandparent universe contained a black hole that collapsed and became the white hole whose interior is our cosmos. Our universe will eventually produce its own black holes. It already has billions of them, each potentially spawning offspring universes where different versions of physics govern different versions of reality. The thought is dizzying in its implications. You're not merely descended from the Big Bang, but from whatever preceded the Big Bang, from whatever collapsed to produce the white hole emergence we call cosmic origin. Your ancestry extends beyond the observable universe, beyond the beginning of time as we measure it, into a chain of cosmic generations that might stretch back infinitely. Let the vertigo wash over you gently. There is no need to hold on to solid ground because, in this picture, solid ground is itself floating on the consequences of infinite cosmic ancestry. Your bed is stable enough for tonight's purposes. Carlo Rovelli's office at the Centre de Physique Théorique in Marseille has a view of the Mediterranean, which seems appropriate for someone whose theoretical work concerns equally vast blue expanses of possibility. Rovelli is one of the founding figures of loop quantum gravity, a candidate theory for quantum gravity that offers specific, startling predictions about what happens at singularities. And those predictions include the claim that black holes eventually become white holes. You have been patient with abstractions tonight, so let us reward that patience with something concrete. Picture a star, massive and luminous, burning through its nuclear fuel over millions of years. Eventually the fuel runs out. The outward pressure that held the star against its own gravity disappears. The core collapses, and if the star is massive enough, that collapse continues past the white dwarf stage, past the neutron star stage, all the way to a black hole. A singularity forms. An event horizon surrounds it. To external observers, the star has become a dark sphere from which nothing escapes. Now wait for an extraordinarily long time. According to Rovelli and his collaborators, something remarkable eventually happens. Quantum mechanics forbids certain configurations that classical physics permits. You cannot, for instance, squeeze an electron into an arbitrarily small space without paying an enormous energy cost. The uncertainty principle demands that confining a particle's position increases the uncertainty in its momentum, and that uncertainty manifests as energy. Push hard enough, and the particle pushes back. Loop quantum gravity extends this principle to space-time itself. Space, in this theory, is not infinitely divisible. There exists a minimum length, a quantum of space below which further division is impossible. When collapsing matter approaches this minimum scale, it cannot compress further. The geometry of space-time reaches a limit and, having nowhere else to go, bounces. The bounce is not instantaneous. From the perspective of an outside observer, it takes an inconceivably long time. We're talking about durations that dwarf the current age of the universe, timescales that make 13.8 billion years look like a brief commercial interruption. The reason involves the extreme time dilation near black hole horizons. Events that happen quickly in the black hole's interior are stretched, from the outside perspective, across eons. Here is a mainstream historical fact that provides context. Loop quantum gravity emerged in the 1980s and 90s as physicists sought alternatives to string theory for unifying quantum mechanics and general relativity. Where string theory proposes that fundamental entities are tiny vibrating strings, loop quantum gravity proposes that space-time itself has a discrete, granular structure at the smallest scales. Both approaches remain speculative, neither having achieved definitive experimental confirmation, but both offer specific predictions about conditions near singularities. Scholars still argue whether loop quantum gravity's predictions about black-to-white hole transitions will ever be testable. The timescales involved are so vast that we cannot simply wait and watch. Some researchers have suggested that primordial black holes, hypothetical small black holes that might have formed in the early universe, could have already completed their transitions and might be detectable as brief gamma-ray bursts. The search continues, inconclusively so far. Rovelli himself has written beautifully about the philosophical implications of his work. In his view, the quantum bounce at a black hole's core is not merely a technical detail, but a profound statement about the nature of time and causality. The matter that falls into a black hole does not cease to exist. It transforms, waits, and eventually re-emerges. Information is preserved, not destroyed. The universe maintains its bookkeeping even in the most extreme circumstances. A quirky detail adds texture to this picture. The bounce might look nearly instantaneous from the perspective of matter falling through the black hole. You drop through the event horizon, accelerate toward the singularity, experience the quantum bounce, and emerge through a white hole, all in what feels like moments. Meanwhile, from the perspective of the universe outside, trillions upon trillions of years have elapsed. Your friends aged and died and crumbled to dust while you were experiencing a brief elevator ride through cosmic geometry. This time, asymmetry is part of what makes the black-to-white hole transition so strange. The interior experience and the exterior experience are drastically different, yet both are valid descriptions of the same physical process. Relativity has always told us that time is personal, that different observers can disagree about durations and simultaneity. The black-to-white hole transition pushes this lesson to its extreme. The relevance to our white hole origin hypothesis is direct. If black holes can bounce into white holes, then our universe might be such a bounce. Whatever collapsed in some parent cosmos, perhaps a black hole, perhaps something more exotic, reached its quantum limit and exploded outward as the Big Bang. We're living in the post-bounce expansion, surrounded by matter that once compressed beyond comprehension and is now spreading toward cosmic dilution. Your muscles have probably relaxed by now, releasing the tensions accumulated through the day. The bounce happens at all scales, if you think about it metaphorically. The compression of waking life, the demands and stresses that squeeze you into tight configurations, reach their limit and you bounce outward into the expansion of sleep. Rest is your personal white hole emergence, a transition from collapsed stress to expanding relaxation. The metaphor is imperfect, as all metaphors are, but it captures something true about rhythms, about the alternation between compression and expansion that characterizes physical systems at every scale. Tonight, you're on the expansion side of your personal cycle, spreading into the softness of rest. Time moves strangely near horizons. You have perhaps heard this claim before, associated with black holes and science fiction scenarios, but the strangeness runs deeper than popular accounts usually convey. Near a white hole's event horizon, time dilation becomes so extreme that the very concept of simultaneity dissolves into ambiguity. What does it mean to say that two events happen at the same time when time itself stretches and compresses depending on where you stand? You're lying still, experiencing time at approximately 1 second per second. This seems obvious, even tautological, but it represents a specific rate determined by your position in space-time. Were you falling toward a black hole, your time would tick differently. An external observer watching you fall would see your clock slow down, your movements becoming sluggish, your descent appearing to freeze as you approach the event horizon. From your perspective, everything would seem normal. You would fall through the horizon without noticing anything special, but the two experiences would be fundamentally irreconcilable. White holes reverse this picture in disorienting ways. Matter emerging from a white hole experiences time normally, streaming outward at tremendous velocities, but external observers attempting to watch this emergence face paradoxes. How long ago did the emergence begin? The question has no simple answer. The time dilation near the horizon stretches the emergence across potentially infinite external time. Matter that emerged moments ago from its own perspective appears to have been emerging forever from the external perspective. This temporal complexity is one reason physicists have struggled to make sense of white holes. With black holes, the time dilation creates dramatic but ultimately consistent pictures. An external observer can model what happens to infalling matter, even if they can never directly observe it. The mathematics hangs together. With white holes, the situation is messier. The emergence from a past singularity creates logical tangles that have never been fully resolved. Here is a mainstream historical fact worth noting. The study of time dilation near event horizons began in earnest with the 1960s work of physicists like John Wheeler, who actually coined the term black hole. Wheeler was famous for his vivid language and his willingness to embrace the counterintuitive implications of general relativity. He encouraged generations of students to take the equations seriously, even when they predicted phenomena that seemed impossible. Scholars still argue about Wheeler's broader philosophical legacy. Was he primarily a physicist who used colourful language for pedagogical purposes, or was he a natural philosopher who happened to express himself through equations? His famous phrase, "space-time tells matter how to move, matter tells space-time how to curve," captures general relativity's essence in a single sentence. But it also suggests a worldview in which reality is far stranger than everyday experience implies. A quirky fringe detail connects time dilation to the white hole hypothesis of cosmic origins. If our universe emerged from a white hole, the time dilation near that emergence would have been extreme. What looks to us like 13.8 billion years of cosmic history might correspond to very different durations from perspectives outside our universe, if such perspectives even make sense. The parent universe, the cosmos whose black hole collapsed to produce our white hole Big Bang, might have experienced our entire history as a brief flash, or as an eternity, or as something for which no temporal description applies. The concept of simultaneity breaks down entirely in such scenarios. When you ask what is happening right now in the parent universe, You're assuming that right now has meaning across the boundary between cosmos. It probably does not. Time in our universe is our time, measured by clocks embedded in our space-time fabric. Whatever time means in the parent universe, if it even means anything, need not correspond to ours. This dissolution of simultaneity is deeply troubling if you crave certainty, and deeply liberating if you can accept ambiguity. The universe is not obligated to make sense according to your intuitions. It simply is, following rules that we partially understand and partially glimpse through mathematical shadows. Our sense that time flows uniformly, that events can be unambiguously ordered, that now means something definite. All of this is an approximation valid in our everyday circumstances, but breaking down under extreme conditions. You're approaching extreme conditions of a different sort, the boundary between waking and sleeping. The transition from consciousness to unconsciousness involves its own temporal strangeness. Dreams compress and stretch time unpredictably. A dream that seems to last hours might occupy minutes of a REM sleep. A momentary hypnic jerk might feel like falling through infinite space. Your personal experience of time is about to become unreliable, which is perfectly fine because reliability was always an illusion anyway. Let your grip on clock time loosen. There is no particular place you need to be tomorrow until tomorrow arrives, and tomorrow is not yet defined. The present moment, this breath you're taking right now, is the only moment guaranteed to exist. The past is memory. The future is anticipation. Only now is actual, and even now slips away as you reach for it, replaced by a slightly later now that is equally fleeting. Cosmic time and personal time flow at their own paces, largely indifferent to each other. The universe does not care about your schedule. Your schedule does not affect the universe's expansion. Both proceed according to their natures, intersecting briefly in this strange phenomenon we call a life, a consciousness, a moment of awareness embedded in 14 billion years of cosmic history. Wormholes connect the cosmic plumbing in ways that seem to belong more to science fiction than to serious physics. Yet these hypothetical tunnels through space-time emerge directly from Einstein's equations, discovered in 1935 by Einstein himself, along with his collaborator Nathan Rosen. The Einstein-Rosen bridge, as it became known, suggests that black holes and white holes might be two ends of the same structure, connected through a throat of warped space-time that bypasses ordinary distance. You can picture this perhaps by imagining a sheet of paper. On one side, draw a point representing a black hole. On the other side, draw another point representing a white hole. Now fold the paper so that the 2 points touch, and imagine a tube connecting them through the fold. Matter falling into the black hole might, in principle, travel through this tube and emerge from the white hole. The distance through the tube could be much shorter than the distance along the paper's surface. This is a wormhole, and it raises questions as provocative as any in physics. Could matter or information travel through these tunnels? Could you use a wormhole to move between distant regions of the universe faster than light could travel through normal space? Could you, in principle, use a wormhole to travel between different universes entirely? The short answers are probably no, and maybe. But the long answers are considerably more interesting, and they connect directly to our question about whether the Big Bang was a white hole. Here is a mainstream historical fact. The Einstein-Rosen paper was not primarily about space travel or cosmic connections. Einstein and Rosen were trying to construct a geometric model of particles, hoping to show that what we call elementary particles might actually be geometric features of space-time, rather than independent objects embedded in space-time. The wormhole emerged as a side effect of this geometric program, an unexpected consequence of the mathematics they were exploring. Einstein never believed wormholes could be used for transportation. He viewed them as mathematical curiosities, interesting artifacts of the equations but not physically meaningful structures. The throats of Einstein-Rosen bridges, it turns out, are unstable. They collapse so quickly that nothing, not even light, could traverse them before they pinch off. The connection between the black hole and white hole ends exists, mathematically speaking, but is too fragile to actually use. Scholars still argue whether more sophisticated wormhole configurations might be stable. In the 1980s, physicist Kip Thorne and his students explored wormholes held open by exotic matter, hypothetical material with negative energy density. Such exotic matter might prevent the throat from collapsing, allowing stable passages between distant regions. Unfortunately, we have no idea how to create exotic matter in the quantities required, and some physicists argue that it cannot exist at all. A quirky detail connects wormholes to the black hole information paradox, one of the most vexing problems in theoretical physics. When matter falls into a black hole, it seems to vanish from the universe, carrying its information with it. If the black hole eventually evaporates through Hawking radiation, what happens to that information? Is it truly destroyed, violating a fundamental principle of quantum mechanics? Or is it somehow encoded in the radiation, preserved in ways we do not yet understand? Some physicists have proposed that wormholes might resolve this paradox. Perhaps information falling into a black hole does not vanish, but travels through a wormhole to emerge elsewhere, possibly in another universe. Possibly in the far future of our own universe, possibly through a white hole. The black hole and the white hole become linked not just geometrically but informationally, with every bit of data that enters one eventually exiting the other. The relevance to cosmic origins is tantalizing. If our universe emerged from a white hole, and if that white hole is connected to a black hole in some parent universe, then information from the parent universe might have travelled through to ours. The physical constants that govern our cosmos, the initial conditions that determined how matter distributed itself after the Big Bang, might be inheritances from elsewhere, passed down through the cosmic plumbing of wormhole connections. This is speculative in the extreme, and you should not mistake speculation for established science. But the speculation is not arbitrary. It emerges from taking the mathematics of general relativity seriously, from following the equations where they lead, from asking what happens if the structures permitted by our best theories actually exist. Sometimes speculation is the only honest response to genuine ignorance. You're warm and comfortable now, hopefully, wrapped in the familiar geometry of your sleeping space. The wormholes we have been discussing are cold mathematical objects, defined by curvature and topology rather than temperature and texture. But they share something with your bed. Both are spaces designed for transition, for passage from one state to another. Your bed carries you from wakefulness to sleep. Wormholes, if they exist, carry matter from one cosmos to another. The passage is never quite what you expect. Sleep brings dreams whose logic defies waking analysis. Wormholes, presumably, would bring experiences equally incomprehensible. Passages through regions where space and time twist in ways no human has ever encountered. But both passages are natural, permitted by the underlying physics of their respective domains. You were made for sleep. The equations were made for wormholes. Both do what they were structured to do. The absence of white holes from our astronomical catalogues demands explanation. If the equations permit them, if they are mathematically as valid as black holes, why have we never observed one? You've been patient with increasingly exotic possibilities tonight, so let us spend some time with the skeptics, with the physicists who doubt that white holes exist anywhere but in equations. The most straightforward objection concerns formation. Black holes form through known processes. When massive stars exhaust their nuclear fuel, their cores collapse. When galaxies evolve, matter accumulates at their centers, eventually compressing into supermassive black holes. The universe is filled with mechanisms for creating black holes, and we've observed the results. Stellar mass black holes detected through their gravitational effects on companion stars, supermassive black holes photographed through radio telescope arrays, merging black holes detected through gravitational waves. White holes have no known formation mechanism. What process would create a region of space-time from which matter constantly flows outward? Stellar collapse produces black holes, not white holes. Gravitational accumulation produces black holes, not white holes. Every natural process we understand involves matter falling together, not matter exploding apart, at least on the scale of gravitational collapse. Here is a mainstream historical fact that shapes the discussion. The detection of gravitational waves in 2015 opened a new window onto black hole physics. The LIGO observatories detected the characteristic chirp of two black holes spiraling together and merging, exactly as general relativity predicted. Since then, dozens of black hole mergers have been detected. The universe is full of black holes, doing exactly what black holes are expected to do. The equivalent signal for white holes, whatever that would sound like, has never been detected. Scholars still argue whether the absence of evidence constitutes evidence of absence in this case. Perhaps white holes exist but are extraordinarily rare. Perhaps they exist only in extreme circumstances, like the origin of universes, where formation mechanisms are entirely different from anything we observe in established cosmos. Perhaps our instruments are simply not designed to detect them. A quirky fringe consideration adds another layer to the skepticism. White holes, if they existed as localized objects in ordinary spacetime, would be thermodynamic nightmares. The second law of thermodynamics states that entropy, the measure of disorder in a system, tends to increase over time. Black holes, it turns out, are entropy champions, containing more entropy than any other object of comparable size. They are thermodynamically sensible, representing endpoints of gravitational collapse where disorder is maximized. White holes would be the opposite, sources of highly ordered matter emerging from singular points. They would decrease the entropy of their surroundings, pumping organized energy into the universe like cosmic air conditioners. This seems to violate everything we know about thermodynamics, about the arrow of time, about the tendency of systems to run down rather than wind up. The thermodynamic objection is serious but not necessarily fatal. Remember that the Big Bang itself was a low-entropy event. The early universe was remarkably ordered, remarkably uniform, remarkably far from thermal equilibrium. That initial order is the reservoir from which all subsequent disorder has flowed. Stars form and burn because the universe began in a special low-entropy state. Life exists because there was free energy to exploit, gradients to mine. If the Big Bang was a white hole, then at least one white hole managed to exist, pouring low-entropy matter into a universe that has been increasing its disorder ever since. The thermodynamic objection might tell us that localized white holes are impossible in an established cosmos, but it does not necessarily apply to the cosmic origin event itself. The instability argument is perhaps the most devastating. Even if a white hole somehow formed, calculations suggest it would immediately become a black hole. The outpouring matter would curve space-time around itself, creating an event horizon that would trap subsequent emissions. The white hole would essentially swallow its own output, converting from a source to a sink in an instant. This instability means that white holes, if they exist at all, would exist only momentarily. They would flicker into being and immediately transform into their opposites. You would never have time to observe one, never have time to catalogue its properties, never have time to do anything but calculate its transition, unless, again, the Big Bang was different. Perhaps a universe-sized white hole is stable in ways that localized white holes are not. Perhaps the lack of external space-time, the absence of surroundings into which the output could curve back, prevents the instability from operating. Perhaps we are living proof that at least one white hole has persisted for billions of years, expanding peacefully without collapsing into self-contradiction. Your skepticism about these ideas is warranted and healthy. Good science maintains appropriate doubt, but doubt is not the same as dismissal. The white hole hypothesis for cosmic origins remains live, investigated by serious researchers, not yet proven and not yet abandoned. You can hold the uncertainty gently as you drift towards sleep. The second law of thermodynamics creates genuine problems for white holes, problems that cannot be dismissed with a wave of the hand. You have perhaps heard of entropy before, that quantity measuring disorder or randomness in a system, but its implications for cosmic origins deserve careful attention. The universe we observe is running down, becoming more disordered, moving from organized beginnings toward chaotic endings. White holes seem to push in the wrong direction. Consider an ice cube melting in a glass of water. The ice cube is ordered, with water molecules locked into crystalline positions. The liquid water is less ordered, with molecules tumbling freely. As the ice melts, order decreases and entropy increases. The second law tells us this is the natural direction, the direction time flows, the direction of thermodynamic destiny. Now imagine watching the ice cube unmelt. Water molecules spontaneously organize, warmth flows from cold to hot. The ice cube reforms from the puddle. This never happens. The second law forbids it, not through some fundamental impossibility, but through overwhelming improbability. The number of disordered states vastly exceeds the number of ordered states, so random molecular motions essentially never produce spontaneous ordering. White holes would be like unmelting ice cubes on a cosmic scale. They would take the disorder of singularities and convert it into the order of outflowing matter. They would pump low entropy energy into high entropy surroundings. They would be thermodynamic refrigerators without external power sources, apparent violations of everything we know about how energy and disorder work. Here is a mainstream historical fact that shapes our understanding. The connection between black holes and thermodynamics was one of the great discoveries of 20th century physics. In the early 1970s, Jacob Bekenstein proposed that black holes carry entropy proportional to their surface area. Stephen Hawking initially resisted this idea, but eventually demonstrated that black holes emit radiation with a specific temperature, cementing the thermodynamic interpretation. Black holes are not just gravitational objects, but thermodynamic objects, participating in energy flows and entropy increases like everything else. Scholars still argue about the deepest implications of black hole thermodynamics. Does the entropy of a black hole represent information stored at its event horizon? Is the holographic principle, the idea that all information in a volume can be encoded on its boundary, a fundamental feature of reality? These questions remain open, investigated by researchers who suspect the answers will reshape our understanding of space, time, and quantum mechanics. A quirky detail adds flavour to the thermodynamic puzzle. When a star collapses into a black hole, its entropy increases dramatically. A star might have an entropy of perhaps 10 to the 20th power in appropriate units. The black hole it forms has an entropy of perhaps 10 to the 77th power. The increase is staggering, by a factor of more than 50 orders of magnitude. Black holes are entropy amplifiers of almost incomprehensible power. White holes would be entropy reversers of equal incomprehensibility. They would take the disorder of singularities and produce the order of outflowing matter. The thermodynamic books would not balance. The universe would owe an entropy debt with no apparent creditor. And yet the Big Bang presents a similar puzzle. The early universe was remarkably ordered, remarkably uniform, remarkably low in entropy despite emerging from a singularity. Cosmologists call this the past hypothesis, the assumption that the early universe was in a special low entropy state. Without this hypothesis, statistical mechanics would predict that we should observe high-entropy messes rather than the structured cosmos we actually see. No one fully understands why the early universe was ordered. Various explanations have been proposed: inflationary cosmology, anthropic selection, fundamental laws we have not yet discovered, but none has achieved consensus. The low entropy of the cosmic beginning is one of the deepest mysteries in physics, a puzzle that should disturb our sleep, except that mysterious things tend to become familiar when we live with them long enough. If the Big Bang was a white hole, then the thermodynamic puzzle remains but takes a specific form. White holes are entropy-reducing objects. The Big Bang was an entropy-reducing event. Perhaps these are connected. Perhaps the low entropy of our cosmic origin is not a coincidence requiring separate explanation, but a consequence of white hole physics. Perhaps white holes are exactly what you need to start a universe, precisely because they produce the ordered initial conditions from which complexity can later emerge. This reasoning is circular at worst, suggestive at best. We do not have a theory of white hole thermodynamics rigorous enough to calculate whether the numbers work out. We have intuitions and analogies and a sense that the puzzle pieces might fit together. But intuitions have been wrong before, and analogies can mislead as easily as enlighten. Your task tonight is not to solve these puzzles, but to appreciate their existence, to recognize that the deepest questions about cosmic origins remain genuinely open. The smartest people in the world have been working on these problems for decades and have not yet converged on answers. You can sit with the uncertainty. You can float in the not knowing. You can let the questions remain questions without feeling obligated to answer them immediately. Stephen Hawking's radiation complicated the picture in ways that reverberate through every discussion of black holes, white holes, and cosmic origins. You might remember Hawking as the physicist who defied motor neuron disease to become one of the most recognizable scientists of the 20th century, communicating through a speech synthesizer while revolutionizing our understanding of space-time. His discovery that black holes emit radiation was one of the most surprising results in the history of physics. The surprise came from quantum mechanics interfering with general relativity at the event horizon. Classical general relativity predicts that nothing escapes a black hole. Quantum mechanics, however, introduces fluctuations even in empty space. Particle-antiparticle pairs pop into existence everywhere, momentarily borrowing energy from the vacuum before annihilating. Usually this virtual pair production has no lasting consequences, but near a black hole's event horizon, something strange happens. One particle of the pair can fall through the horizon while the other escapes. The escaping particle carries real energy that must come from somewhere. It comes from the black hole itself, reducing its mass slightly with each escaped particle. Over time, this process causes black holes to evaporate, shrinking and eventually vanishing in a final burst of radiation. The timescales involved are almost comically long. A stellar mass black hole would take longer than the current age of the universe, raised to a power larger than the current age of the universe, to evaporate. But the principle matters more than the numbers. Black holes are not eternal. They decay. They return their matter and energy to the cosmos, transformed into thermal radiation. Here is a mainstream historical fact. Hawking's 1974 paper on black hole radiation was initially met with skepticism by much of the physics community. The calculation combined quantum field theory and general relativity in ways that had not been done before, and many experts doubted its validity. Over the following decades, independent calculations confirmed Hawking's result, and black hole radiation became an accepted prediction of theoretical physics. Scholars still argue about the information paradox that Hawking radiation creates. If a black hole evaporates completely, what happens to the information about everything that fell in? quantum mechanics demands that information be conserved. You should be able, in principle, to reconstruct any initial state from complete knowledge of the final state. But Hawking radiation appears to be purely thermal, carrying no information about the black hole's history. Where did the information go? Various resolutions have been proposed. Perhaps information escapes through subtle correlations in the Hawking radiation. Perhaps it remains at the singularity, encoded in whatever quantum gravitational structure replaces the classical singularity. Perhaps it travels through wormholes to emerge elsewhere. No consensus has formed, and the information paradox remains one of the most actively researched problems in theoretical physics. A quirky connection links Hawking radiation to white holes. If black holes can evaporate, can white holes form from evaporation running backward? Could the time-reversed Hawking radiation, matter and energy converging from distant regions and falling into a point, create a white hole? The mathematics does not obviously forbid it, but it would require coordinating the trajectories of countless particles with precision that seems thermodynamically impossible. And yet the Big Bang was precisely such a coordinated convergence, viewed from the perspective of time running backward. Play the cosmic expansion in reverse, and you see all matter and radiation converging toward a single point. The motion is coordinated with exactitude that would make any choreographer weep with envy. Thermodynamically improbable? Absolutely. But it happened, or rather, its time reverse happened. We are living in the aftermath of an event that, from certain perspectives, looks like the ultimate thermodynamic miracle. The white hole hypothesis for cosmic origins does not resolve the information paradox, but it reframes it. If our universe emerged from a white hole, and if that white hole was connected to a black hole in a parent universe, then perhaps information from the parent universe flowed through to ours. The black hole in the parent universe collected matter and information over eons. The white hole in our universe released that matter and information at the Big Bang. Conservation is preserved, though across cosmic generations rather than within a single universe. This is speculation layered on speculation, and you should handle it with appropriate caution. But it illustrates how the deepest puzzles in physics connect to each other, how questions about black hole thermodynamics relate to questions about cosmic origins relate to questions about the nature of time and information. The problems are not isolated. They form a web, and pulling on any strand sends vibrations through all the others. Your mind might be forming its own webs now, connections between ideas that had seemed separate, patterns emerging from the accumulating concepts. This is how understanding works, not through sequential absorption of facts, but through gradual recognition of relationships. Let the connections form naturally. Let the web organize itself while you drift toward rest. Our universe's expansion tells stories encoded in red-shifted light and receding galaxies. The evidence surrounds us, invisible to the naked eye but measurable with instruments of sufficient precision. Every distant galaxy shows light stretched toward longer wavelengths, red-shifted by the expansion of space itself. The farther the galaxy, the greater the redshift, exactly as you would expect if space is stretching uniformly throughout the cosmos. This expansion is perhaps the most direct evidence connecting our universe to white hole behavior. Remember that white holes are defined by outward flow, matter and energy streaming away from a central region, unable to return. Our universe exhibits precisely this behavior. Galaxies recede from each other, space stretches. The distance between cosmic structures increases with every passing moment. We're living in an expanding bubble, and the expansion shows no signs of stopping. Edwin Hubble established the expansion observationally in 1929, though theoretical predictions had preceded his measurements. Alexander Friedmann in 1922 and Georges Lemaitre in 1927 had both derived expanding universe solutions from Einstein's equations. Lemaitre even proposed what he called the primeval atom hypothesis, the idea that the universe began as a single dense point that exploded outward. This was the intellectual ancestor of what we now call the Big Bang. Here is a mainstream historical fact worth savouring. Lemaitre was not only a physicist but also a Catholic priest. He saw no contradiction between his faith and his science, viewing the primeval atom as a fitting starting point for creation. Einstein, initially skeptical of expanding universe solutions, eventually accepted the evidence and abandoned his static universe model. The universe was expanding, whether the great minds wanted it to or not. Scholars still argue about the precise relationship between Hubble and Lemaitre, about who deserves credit for the expanding universe discovery, about whether Lemaitre's earlier work was properly recognized during his lifetime. Scientific priority is messy, and retrospective justice is difficult to achieve. What matters for our purposes is that the expansion is real, measured, confirmed by independent methods. The cosmic microwave background provides additional confirmation. This radiation, discovered in 1965 by Arno Penzias and Robert Wilson, is the afterglow of the Big Bang. It fills the universe uniformly, appearing from every direction with nearly identical intensity. Its existence was predicted before its discovery, a consequence of the hot, dense early state implied by cosmic expansion. When you tune a television to an empty channel and see static, a small fraction of that static is cosmic microwave background radiation, ancient light from the universe's infancy, reaching your living room 14 billion years later. A quirky detail adds depth to this picture. The cosmic microwave background is not perfectly uniform. Tiny temperature variations, about 1 part in 100,000, mark the locations where matter was slightly denser or less dense in the early universe. These variations became the seeds of cosmic structure. Regions that were slightly denser attracted more matter, eventually forming galaxies and galaxy clusters. The pattern of variations we observe today tells us about conditions shortly after the Big Bang, about the initial state from which structure grew. If the Big Bang was a white hole, the cosmic microwave background is a snapshot of matter streaming out from that white hole, captured at the moment when the universe became transparent to light. The variations encode the imperfections in the emergence, the quantum fluctuations that shape the white hole's output. We are seeing the fingerprints of cosmic origin, scattered across the sky in microwaves. The distribution of matter in the universe provides further evidence. Galaxies are not scattered randomly. They cluster into groups and superclusters, connected by filaments of matter that span hundreds of millions of light years. Between the filaments lie vast voids, regions almost empty of galaxies. This cosmic web structure emerged from the initial variations in the early universe, amplified by gravity over billions of years. The web structure is compatible with white hole emergence. Matter streaming outward from a central singularity would carry the imprint of quantum variations at the source. Those variations would grow as the universe expanded, seeding the structures we now observe. The cosmic web is thus a record of the Big Bang's initial conditions, a fossil of the emergence that created everything. Your breathing has probably slowed by now, settling into the rhythm of approaching sleep. The universe's expansion has been slowing too, though recently it began accelerating for reasons we still do not fully understand. Dark energy, the mysterious force driving this acceleration, represents about 68% of the universe's total energy content. We have named it and measured its effects, but do not know what it is. The mysteries compound as we examine the cosmos more closely. Dark matter, dark energy, the initial conditions of the Big Bang, the nature of space-time at quantum scales, layers of ignorance beneath our confident claims of knowledge. But the ignorance is structured. We know what we do not know. we can formulate precise questions even when we cannot answer them. This is progress of a certain kind. The cosmic microwave background radiation whispers secrets about the universe's infancy. You have returned from whatever depths of rest you found, or perhaps you never quite departed, hovering in that liminal state between waking and sleeping where words drift in and out like clouds. Either way, welcome back to the continuing exploration of cosmic origins. The microwave background is almost perfectly uniform, the same temperature in every direction to about 1 part in 10,000. This uniformity presents a puzzle that cosmologists call the horizon problem. How did opposite sides of the sky, regions so far apart that light has never had time to travel between them, come to have the same temperature? They cannot have communicated. They cannot have exchanged energy. Yet somehow they agreed on precisely the same conditions. The standard explanation invokes inflation, a period of extraordinarily rapid expansion in the universe's first fraction of a second. During inflation, the universe doubled in size repeatedly, perhaps 60 or more times in succession, growing from smaller than an atom to larger than the observable universe today. Regions that were once close enough to exchange information were suddenly separated by distances too vast for any signal to cross. Here is a mainstream historical fact. Inflationary theory was proposed independently by several physicists in the early 1980s, including Alan Guth, Andre Linde, Andreas Albrecht, and Paul Steinhardt. The theory explained not only the horizon problem but also why the universe appears geometrically flat, and why we do not observe certain exotic particles predicted by early universe physics. Inflation became the dominant paradigm for understanding the first moments of cosmic history. Scholars still argue about whether inflation actually occurred and whether it makes the predictions we claim. Some critics argue that inflationary theory is too flexible, that it can accommodate almost any observation through appropriate choice of parameters. Others argue that inflation creates more puzzles than it solves, particularly concerning the initial conditions required to start inflation in the first place. A quirky connection links inflation to the white hole hypothesis. If the Big Bang was a white hole, the uniform temperature of the cosmic microwave background might have a different explanation. Matter emerging from a white hole singularity would share a common origin, a single point from which everything emerged. The uniformity would be built in from the start rather than established through communication or inflation. This alternative explanation has not been developed with the same mathematical rigor as inflation. It remains suggestive rather than quantitative, a possibility rather than a prediction. But it illustrates how the white hole framework might reframe puzzles that standard cosmology struggles with. The tiny temperature variations in the cosmic microwave background, those 1 part in 100,000 fluctuations, tell an even more interesting story. These variations were first measured in detail by the COBE satellite in 1992 and have been mapped with increasing precision by subsequent missions including WMAP and Planck. The pattern of variations carries information about the physics of the early universe, about the composition of matter and energy, about the geometry of space-time. The variations match the predictions of inflationary theory remarkably well. They have the statistical properties expected from quantum fluctuations, stretched to cosmic scales by inflation. They correlate across angular scales in ways that depend on the universe's composition. The agreement between theory and observation is one of the triumphs of modern cosmology. Whether this triumph supports or undermines the white hole hypothesis is unclear. The quantum fluctuations that seed the variations might have occurred during inflation, as the standard picture suggests. They might also have occurred at the white hole singularity itself, imprinted on outflowing matter as it emerged from the singular origin. Both scenarios predict fluctuations with similar properties, making it difficult to distinguish between them observationally. The cosmic microwave background also carries subtle polarization patterns. Light from the early universe was scattered by electrons, imprinting polarization that encodes information about conditions at the time of scattering. Recently, cosmologists have searched for a specific polarization pattern called B-modes, which would be evidence of gravitational waves from the inflationary epoch. The search for B-modes has been controversial. A 2014 announcement by the BICAP-2 collaboration claimed detection, but subsequent analysis revealed that dust in our galaxy could explain the signal. The primordial B-modes, if they exist, remain hidden beneath galactic contamination. Future experiments might find them, providing strong evidence for inflation, or might continue to find nothing, leaving the question open. You're surrounded by this ancient light even now. The cosmic microwave background permeates all of space, filling every room, passing through every object, present everywhere at approximately 3 degrees above absolute zero. You cannot see it or feel it, but it is there, a bath of radiation left over from the universe's hot, dense beginning. The ubiquity of this radiation is somehow comforting. The universe's oldest light keeps you company, whether you notice it or not. The photons began their journey 13.8 billion years ago and have been wandering ever since, stretched by expansion, cooled by cosmic evolution, but still present, still carrying information about conditions shortly after the beginning. If the beginning was a white hole, these photons are messengers from the emergence. They carry news from the moment matter first escaped the singularity, from the instant space began its expansion, from the birth of everything we know. The news is old, but it is still arriving. The message is faint, but it can still be read. Dark energy might be the strangest clue of all. Since 1998, astronomers have known that the universe's expansion is accelerating, driven by some mysterious force that permeates all of space. This force, dubbed dark energy for lack of a better name, constitutes about 68% of the universe's total energy content. We have named it, measured its effects, and confessed our ignorance about its nature. The discovery came from observations of distant supernovae. Type Ia supernovae are cosmic standard candles, explosions of such consistent brightness that their apparent dimness reveals their distance. In the late 1990s, 2 independent teams studied supernovae at cosmic distances and found them dimmer than expected. The universe was not expanding at a constant rate, or slowing down as matter attracted other matter. It was speeding up. Here is a mainstream historical fact. The discovery of cosmic acceleration earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics. Their finding overturned decades of cosmological expectations and forced physicists to accept that something unknown dominates the universe's energy budget. Einstein's cosmological constant, once abandoned as a blunder, returned as a possible explanation. Scholars still argue about whether dark energy is truly constant or whether it evolves over time. Is dark energy the cosmological constant, a fixed property of space-time itself? Or is it a dynamic field, changing as the universe expands? Observations to date are consistent with a constant, but the measurements are not precise enough to rule out slow evolution. A quirky connection links dark energy to the white hole hypothesis in ways that remain speculative but intriguing. White holes push matter outward, preventing anything from entering. Could the accelerating expansion of the universe be a remnant of white hole dynamics? Could dark energy be the lingering influence of the white hole emergence that created our cosmos? This speculation has not been developed mathematically to the point where it makes specific predictions. It hovers in that uncomfortable zone between inspired guess and wild speculation. But it illustrates how the white hole framework might connect to observed phenomena in ways that standard cosmology does not anticipate. The nature of dark energy relates to deeper questions about space-time itself. Is space genuinely empty in the absence of matter? or does it have its own energy density even when nothing is present? Quantum mechanics suggests that the vacuum is not truly empty. Virtual particles pop in and out of existence. Fluctuations ripple through even completely empty regions. The energy density of these fluctuations should contribute to dark energy. Unfortunately, when physicists calculate the expected vacuum energy density, they get answers that are completely wrong. The predicted energy density exceeds the observed dark energy density by factors of 10 to the power of 120. This is arguably the worst prediction in the history of physics, a disagreement between theory and observation so vast that it suggests something fundamental is missing from our understanding. Various explanations have been proposed. Perhaps symmetries we do not yet understand cancel most of the vacuum energy. Perhaps the calculation itself is flawed in ways we have not recognized. Perhaps dark energy has nothing to do with vacuum fluctuations at all. No consensus is formed. The white hole hypothesis adds another possibility. If our universe emerged from a white hole, the properties of space-time in our cosmos might be inherited from the emergence process rather than calculable from first principles. The dark energy density we observe might be a consequence of how white holes work, determined by the physics of cosmic birth rather than by the physics of empty space. This possibility shifts the question from what is dark energy to why did the white hole produce this particular dark energy density? The question might be more tractable in the white hole framework, or it might be equally intractable. Without a detailed theory of white hole emergence, we cannot say. You are floating in this accelerating cosmos, carried along by the expansion that dark energy drives. Every moment the distance between cosmic structures grows. Every moment distant galaxies recede faster. In the far future, if dark energy continues its dominance, other galaxies will recede beyond our cosmic horizon, leaving us alone in a vast, empty night. This eventual cosmic loneliness lies billions of years in the future, so you need not worry about it tonight. For now, the universe remains full of light, full of structure, full of connections between distant regions. The acceleration is real but gentle, imperceptible on human scales. Your room is not expanding, your bed is not stretching. The forces binding matter together easily overcome the cosmic expansion at local scales. Only at the larger scales across millions of light years does the expansion manifest. There, space stretches faster than gravity can pull matter together. There, the universe's ultimate isolation takes shape. But tonight, you are surrounded by nearness, by the comforting proximity of walls and floors and familiar objects. What existed before the beginning? The question is either profound or meaningless, depending on your philosophical commitments. If time itself began with the Big Bang, then before is a word without referent, pointing at nothing because there was no when for anything to exist in. If time extends beyond our universe, then the question demands an answer, an account of whatever preceded the emergence we call cosmic origin. You've asked similar questions throughout your life, no doubt. What existed before I was born? What exists outside the room I am in? What lies beyond the horizon I can see? These questions have sensible answers. Your parents, other rooms, other places, because the space and time they reference actually exist. The question of what preceded the Big Bang is harder because we genuinely do not know whether there was any such precedent. Classical general relativity offers no help here. The equations break down at singularities, refusing to tell us what happens at time zero or before. The Big Bang singularity is not a point in space-time from which we can look backward. It is a point at which space-time itself becomes undefined. Asking what came before is like asking what is north of the North Pole. The question assumes a framework that does not apply. Here is a mainstream historical fact that shapes modern thinking. In 1983, James Hartle and Stephen Hawking proposed a no-boundary model of the universe's beginning. They suggested that time near the Big Bang might gradually transform into a spatial dimension, eliminating the sharp beginning that traditional cosmology implied. In this model, the universe has no boundary in time, just as the surface of a sphere has no edge. The question of what came before becomes meaningless, because there is no before, only a smooth geometry that looks like time when you are far from the origin. Scholars still argue about whether the no-boundary proposal is mathematically consistent, and whether it makes testable predictions. The proposal requires imaginary time, a mathematical technique where time is treated as an imaginary number, which some view as a powerful tool and others view as a mathematical trick without physical meaning. A quirky alternative connects directly to our white hole theme. If the Big Bang was a white hole, then before the Big Bang might refer to conditions in a parent universe. Whatever collapsed to form the black hole that became our white hole existed in some prior space-time. That prior space-time had its own history, its own physics, its own conditions, before our Big Bang was during their cosmic existence. This reframing does not eliminate the question of ultimate origins. Where did the parent universe come from? If it also emerged from a white hole connected to a grandparent universe, the question recurs. You can push the chain of cosmic ancestry back indefinitely, each universe emerging from a predecessor, but you eventually wonder whether the chain itself has a beginning or extends infinitely into the past. Infinite chains are philosophically troublesome but not logically prohibited. The integers extend infinitely in both directions, and we do not demand that zero be the absolute beginning. Perhaps the chain of universes extends similarly, without a first member, each cosmos preceded by another in an endless regression. The alternative is a first universe, a cosmos that somehow came into being without emerging from anything prior. This first universe would face all the questions about initial conditions that we face about our own Big Bang. Why did it begin? What determined its properties? Why was there something rather than nothing? These questions may have answers or may mark the boundary of what explanations can achieve. At some point the chain of because must terminate. Either the chain extends infinitely, in which case every link has a predecessor, but the chain itself just exists, or the chain has a first link, in which case that first link has no predecessor and simply exists without further explanation. Neither option is entirely satisfying, but those appear to be the choices. You're lying in bed, contemplating origins that extend beyond anything we can observe or test. The contemplation is not idle. It is the fundamental human activity of seeking coherence, of trying to understand how things fit together, of wondering why anything exists at all. The questions have no definitive answers, but the wondering itself has value. The night deepens around you. Whatever existed before your wakefulness, whatever dreams might come, whatever memories fade, will remain inaccessible once sleep arrives. You will emerge from sleep as if from your own personal origin, reconstituting consciousness from the formlessness of rest. The parallel is imperfect but suggestive. Tonight you're experiencing a small-scale version of cosmic mystery. The transition from waking to sleeping is not well understood. The boundary between consciousness and unconsciousness is fuzzy, gradual, uncertain. You cannot report on the moment of transition because you're not there to observe it. You are awake, and then you are not, and the before and after do not quite connect. Perhaps the cosmic before and after are similarly disconnected. Perhaps asking what preceded the Big Bang is like asking what thought preceded sleep, a question that assumes continuity where none exists. Or perhaps the connections are real. The cosmic lineage extends backward, and what came before remains present in what exists now, encoded in the physical constants and initial conditions we inherit from whatever preceded us. Roger Penrose sat in his Oxford office, surrounded by the accumulated papers of a lifetime devoted to mathematical physics, and contemplated eternity. His theory of conformal cyclic cosmology offers an alternative to the white hole hypothesis, a different way of understanding how our universe might connect to whatever preceded it. The theory is audacious, controversial, and beautifully geometric. The basic idea involves the distant future of our universe. As cosmic expansion continues and matter disperses, the universe will eventually become incredibly dilute. Particles will spread so far apart that interactions between them become infinitesimally rare. In the unimaginably far future, the universe will be dominated by radiation, by massless particles travelling at the speed of light. Here is the conceptual trick. For massless particles, time does not pass. The photon that left a star and travelled for 14 billion years to reach your eye did not experience those 14 billion years. For the photon, the emission and absorption were simultaneous. Time, for massless particles, is not a dimension through which they travel, but a feature of the space-time they traverse. In the far future, when all massive particles have decayed and only radiation remains, the universe will consist entirely of entities for which time is meaningless. Penrose suggests that such a universe loses the distinction between large and small, between long durations and short ones. The infinitely old, infinitely large far future becomes indistinguishable from the infinitely small, infinitely brief Big Bang. Here is a mainstream historical fact. Penrose first presented conformal cyclic cosmology in the early 2000s, building on mathematical insights from his earlier work on singularity theorems and twistor theory. The proposal attracted attention both for its elegance and for its apparent testability. Penrose claimed that patterns in the cosmic microwave background might reveal signatures of events from a previous cosmic aeon, with gravitational waves from colliding black holes in the prior universe, leaving imprints detectable today. Scholars still argue about whether Penrose's claimed signatures actually exist. Several studies have searched for the predicted patterns with conflicting results. Some researchers claim to see the signatures, others find only statistical noise. The debate continues with no clear resolution in sight. A quirky aspect of conformal cyclic cosmology involves the loss of information between aeons. In the transition from one aeon to the next, the detailed information about the previous aeon's contents is erased or transformed beyond recognition. Only certain large-scale features survive, gravitational wave signatures perhaps, or the general geometry of space-time. The fine details, the positions and velocities of all particles vanish into the conformal transformation. The relationship between Penrose's proposal and the white hole hypothesis is subtle. Both suggest that our universe connects to something prior, but they imagine that connection differently. The white hole hypothesis proposes a birth event, matter and energy emerging from a singularity that formed when something collapsed elsewhere. Conformal cyclic cosmology proposes a smooth transition, one aeon flowing into the next through a geometric transformation rather than a violent emergence. These alternatives are not necessarily mutually exclusive. Perhaps different regions of reality operate according to different principles. Perhaps some universes emerge from white holes, while others transition through conformal mappings. Perhaps the truth involves elements of both pictures in ways we have not yet imagined. Penrose's mathematics is beautiful, whatever its physical validity. The conformal transformations he invokes are elegant operations that preserve angles while distorting scales. The idea that physical reality might undergo such transformations, that the vast and the minuscule might be two faces of the same geometric coin, speaks to deep aesthetic sensibilities in physics. Nature loves symmetry, and conformal symmetry is among the most powerful and beautiful. You do not need to understand the mathematics to appreciate the vision. An eternal cosmos, cycling through aeons, each beginning connected to the previous ending, No first cause required because the chain loops back on itself. The universe is a strange loop, an eternal recurrence of beginnings that are also endings. Or perhaps the universe is more tree-like, branching rather than cycling, with each black hole collapse producing a new universe whose black holes produce further universes. The white hole hypothesis suggests proliferation rather than recurrence, cosmic ancestry rather than cosmic cycles. Both visions have their appeal. The cycle promises that nothing is truly lost, that everything returns in transformed form. The tree promises that everything is a new beginning, that each universe is genuinely novel rather than a repetition of patterns. Perhaps neither vision is correct. Perhaps the ultimate story of cosmic origins involves concepts we have not yet imagined, using mathematics not yet invented, answering questions we have not yet learned to ask. The history of physics has been a series of surprises, each breakthrough revealing that reality was stranger than anyone guessed. Future breakthroughs will likely continue this pattern. Your task is not to anticipate those breakthroughs, but to appreciate the questions as they currently stand. Tonight, you're holding multiple possibilities without forcing premature resolution. You're allowing uncertainty to coexist with curiosity. This is the scientific temperament at its best, the willingness to not know while continuing to wonder. Testing the untestable seems like a contradiction, yet theoretical physicists spend considerable effort devising ways to confirm or refute hypotheses that appear beyond empirical reach. The white hole hypothesis for cosmic origins has long seemed untestable, but recent developments suggest that might change. Gravitational waves, cosmic microwave background details, and perhaps other observations might eventually distinguish between different theories of the Big Bang. Gravitational wave astronomy began in earnest with the 2015 detection by LIGO. Those ripples in space-time produced by merging black holes opened a new window onto the universe. Since then, dozens of mergers have been detected, each providing information about black hole populations, about the dynamics of binary systems, about the nature of space-time itself. Here is a mainstream historical fact. The existence of gravitational waves was predicted by Einstein in 1916, but their detection required a century of technological development. The LIGO detectors measure changes in distance 1,000 times smaller than the diameter of a proton, achieving sensitivities that seemed impossible when the project began. The 2017 Nobel Prize in Physics recognized the achievement. Scholars still argue about what gravitational wave astronomy will ultimately reveal. Some researchers hope to detect gravitational waves from the very early universe, from inflation, or perhaps from the Big Bang itself. These primordial gravitational waves would carry information about conditions inaccessible through any other means, potentially distinguishing between different theories of cosmic origins. A quirky possibility involves gravitational wave signatures specific to white hole emergence. If the Big Bang was a white hole, the violent dynamics of that emergence might have produced gravitational waves with characteristic properties, specific frequencies, specific polarizations, specific spatial patterns. No one has calculated these properties with precision, but the calculation is in principle possible. The cosmic microwave background offers another avenue. We discussed the tiny temperature variations earlier, the 1 part in 100,000 fluctuations that seeded cosmic structure. The statistical properties of these fluctuations depend on the physics of the early universe. Different theories of cosmic origins predict different statistical patterns. Current observations are consistent with inflation, but they are also consistent with other possibilities. The measurements are precise but not definitive. Future experiments might achieve the precision needed to distinguish between theories, or they might continue to find results consistent with multiple frameworks. This search for primordial B-modes in cosmic microwave background polarization continues. If detected, These polarization patterns would provide strong evidence for gravitational waves from the early universe, supporting inflationary theory. If not detected despite increasingly sensitive searches, theorists would need to explain their absence, potentially opening space for alternative theories including white hole emergence. Particle physics might also contribute. The Large Hadron Collider and future accelerators probe energy scales approaching those relevant to the early universe. Discoveries about fundamental particles and forces constrain theories of cosmic origins. If new particles or forces are discovered, they would need to be incorporated into any successful theory of the Big Bang. The theoretical side of the enterprise involves developing white hole emergence models with sufficient rigor to make precise predictions. Currently, the white hole hypothesis is more of a framework than a theory, a general idea that suggests certain patterns without specifying them in detail. Converting this framework into a theory requires mathematical work that has not yet been completed. Loop quantum gravity, as we discussed earlier, provides one possible foundation. Carlo, Rovelli and colleagues have developed models in which black holes bounce into white holes through quantum gravitational effects. Extending these models to the cosmological scale, applying them to the Big Bang rather than to stellar mass black holes, is ongoing work. The testing of cosmological theories is always indirect. We cannot travel to the Big Bang, cannot observe the singularity directly, cannot perform experiments at the relevant energy scales. Instead, we look for fingerprints, for consequences of primordial conditions that persist in today's observable universe. The cosmic microwave background, the distribution of galaxies, the abundance of light elements, gravitational waves, all carry information about the early universe, encoded in forms we can partially decode. You are part of this decoding effort in a sense. By listening, by wondering, by holding the questions in your mind, you participate in the human endeavor to understand origins. You will not discover the answer tonight. No one will discover the answer tonight. But the wondering matters. The questions shape future research, and future research might eventually converge on answers. The night is long, and the questions are patient. They have waited billions of years to be asked and can wait a while longer to be answered. Let them rest beside you as you rest. Our place in the cosmic family becomes clearer as the picture develops. If the white hole hypothesis is correct, we are not merely inhabitants of a universe, but descendants of a lineage extending beyond our universe's boundaries. The chain of cosmic ancestry connects us to whatever collapsed to produce our emergence, and connects that predecessor to whatever preceded it, and so on through generations we cannot count and perhaps cannot imagine. You have a family tree, roots extending back through human history, through primate evolution, through the emergence of life, through planetary formation, through stellar nucleosynthesis. The white hole hypothesis extends this tree further, back through cosmic origins to prior universes whose physics we might never understand. Here is a mainstream historical fact that grounds this speculation. The multiverse concept, the idea that our universe might be one among many, has become increasingly respectable in mainstream physics. Inflationary cosmology naturally produces multiple universes, each with potentially different physical constants. String theory predicts a vast landscape of possible vacuum states, each defining a different universe. The white hole hypothesis adds another mechanism for cosmic proliferation, another way for the multiverse to generate diversity. Scholars still argue about whether multiverse theories are scientifically legitimate. If other universes are by definition causally disconnected from ours, how can we ever test theories about them? Some argue that explanatory power justifies multiverse theories even without direct tests. Others argue that untestable theories belong to philosophy or metaphysics rather than physics. A quirky consideration involves the inheritance of physical constants. If our universe emerged from a white hole connected to a black hole in a parent universe, We might have inherited our physical constants from that parent. The mass of the electron, the strength of gravity, the speed of light. These might not be fundamental values determined by mathematical necessity, but inherited values passed down through cosmic generations. Smolin's cosmological natural selection takes this inheritance idea seriously. In his picture, physical constants vary slightly from generation to generation, with universes that produce many black holes outcompeting those that produce few. Over cosmic generations, the physical constants evolve toward values that maximize black hole production. Whether our observed constants actually maximize black hole production is debated. Smolin has argued that they do, that small changes in most constants would reduce rather than increase the number of black holes our universe produces. Critics have questioned these arguments, proposing alternative constant changes that might increase black hole formation without destabilizing other aspects of physics. The debate is difficult to resolve because we have only one universe to observe. Statistical claims about the distribution of physical constants across a multiverse require comparing many universes, but we have access only to our own. We can ask whether our constants are special, whether they seem fine-tuned for any particular outcome, but we cannot directly measure what constants other universes might have. The philosophical implications of cosmic ancestry are profound. If we are descended from prior universes, our existence is contingent in ways that extend beyond evolutionary biology. Not only did specific events in Earth's history have to occur for you to exist, but specific events in a prior universe's history had to occur for our universe to exist at all. The chain of contingency extends beyond observable reality. This contingency is either humbling or empowering depending on your perspective. Humbling because it reveals how dependent you are on conditions you did not create and cannot control. Empowering because it reveals how remarkable your existence is, how many coincidences had to coincide for consciousness to emerge and wonder about its origins. You are rare. Even if universes are common, even if the multiverse contains countless cosmos, the particular configuration of matter that produces you exists only here, only now, only in this specific corner of this specific universe. The white hole that birthed our cosmos set in motion the processes that eventually produced your awareness, your memories, your curiosity about cosmic questions. Let this rarity sit gently with you. You're not obligated to feel special or to draw grand conclusions from your uniqueness. The facts are the facts regardless of how you interpret them. But if the interpretation provides comfort or wonder or gratitude, let it provide those things. The night holds you. The cosmic lineage extends beyond you in both directions, toward the ancestors you can never observe, and toward the descendants who might eventually emerge from whatever black holes our universe produces. You're one link in a chain, one moment in a sequence, one observer in a cosmos that mostly lacks observers. The silence of the night is not truly silent. It is filled with cosmic microwave background radiation, with gravitational waves too weak to detect without instruments, with neutrinos passing through your body by the trillions every second. The universe is busy even when your surroundings are quiet. Drifting now into infinite possibility, you find that the boundaries between certainty and speculation blur like the edge of sleep itself. The white hole hypothesis remains unproven, but its possibility has expanded your sense of what the cosmos might be. The questions we've explored tonight do not demand immediate answers. They can float beside you, companions to whatever dreams might come. The journey from Einstein's equations to cosmic ancestry has been winding but coherent. Each step built on the previous, each concept connecting to others in a web of implications. Black holes collapsing, white holes emerging, singularities marking the limits of our theories, time dilation stretching ordinary experience beyond recognition. The picture is not complete, but its outlines have become visible. Here is a mainstream historical fact to carry with you. The study of cosmic origins has transformed over the past century from speculation to science. Questions that seemed forever unanswerable have yielded to observation and mathematics. The cosmic microwave background, once unknown, now tells us about conditions 13.8 billion years ago. Gravitational waves, once theoretical, now reveal black hole mergers across cosmic distances. The pace of discovery suggests that future surprises await. Scholars still argue about nearly everything we have discussed. The white hole hypothesis, cosmological natural selection, loop quantum gravity, conformal cyclic cosmology, all remain active areas of research without consensus conclusions. This is the nature of science at the frontier, where certainty gives way to investigation and answers remain provisional. A quirky comfort emerges from this uncertainty. If all questions were answered, there would be nothing left to wonder about. The mysteries that remain are gifts, invitations to curiosity, reasons to pay attention. The universe has not yet revealed all its secrets, which means discovery remains possible. Your place in this cosmos is simultaneously insignificant and remarkable. Insignificant because the universe is vast beyond comprehension, containing more stars than grains of sand on all Earth's beaches, extending for billions of light years in every direction. Remarkable because you exist at all, because matter organized itself into consciousness, because atoms arranged themselves into entities capable of wondering about their origins. The white hole that might have birthed our universe did not intend you. There was no plan, no design, no purpose built into the emergence. But here you are nonetheless, a consequence of physical processes playing out over cosmic time, an unexpected result of equations that know nothing of your existence. Let this thought accompany you into sleep. You are the universe contemplating itself, matter wondering about matter, a temporary arrangement of atoms asking how arrangements come to be. The questions are ancient, but your asking of them is new. No one has ever asked these questions in quite the way you've asked them tonight. The cycle of questioning and resting will continue. Tomorrow you will wake, emerging perhaps like a small-scale white hole, consciousness arising from the mystery of sleep. The day will bring its demands, and the cosmic questions will retreat to the background. But they will remain, waiting for the next opportunity to be considered. Tonight they have been considered. Tonight you have held possibilities in your mind without forcing premature resolution. Tonight you have wandered through speculation and evidence, through mathematics and metaphor, through the strange territory where physics meets philosophy. Your breathing is slow now. Your muscles are relaxed. Your mind is releasing its grip on wakefulness, allowing the transition that happens every night to proceed. The transition is mysterious, as mysterious in its way as the transition from nothing to everything that we call the Big Bang. Let the mystery be. Let the questions rest. Let the cosmos continue its expansion while you contract into sleep, while your awareness folds inward, while the boundaries of self become indistinct. The white hole of cosmic origins is almost inconceivably distant in time and space, but you are inside it still if the hypothesis is correct. Its expansion continues, and you are part of that expansion, even as you hold still tonight. Even stillness is motion when viewed from the right perspective. Even rest is activity when the background is cosmic expansion. You are never truly motionless, never truly separate from the processes that created you. Tonight, you have traced some of those processes backward, toward origins you cannot directly observe. Tomorrow, you will participate in processes that point forward, toward consequences you cannot predict. The arrow of time carries you from past to future, from memory to anticipation, from waking through sleeping to waking again. Let the arrow carry you now. Let the transition happen. Let consciousness release its hold and trust that awareness will return, as it has returned every morning of your life. The cosmos will not miss you while you sleep. It has been expanding for billions of years without your attention and will continue after you rest. But when you wake, the cosmos will be there, still expanding, still mysterious, still offering questions for those willing to ask. Sweet dreams,